All right. So good. I don't know where you are. So in my case, in Japan, it's already midnight. So good evening for everybody. And for those of you in Europe, it's good afternoon. My name is Nobuyuki Hanai. I was a former colleague of Alan who was just speaking at the plenary. And I will be speaking about heterogeneity. That one of the big issue, one of the topic Alan mentioned quickly. But I'm gonna approach the heterogeneity from a cognitive ability perspective. And, all right. So this presentation is based on my recent article that's published in Japanese Economic Review because I gave a keynote speech at the Japanese Economic Association last 2 years ago. And so if you're interested, you can search for this article to know more about what I'm going to say. But if you don't follow what I'm going to say, just ask me a question. I thought this is an interactive session, right? So I hope people can ask questions. And in particular, I'm going to be talking about 3 papers that I have written in past 5 years. So what I'm going to show is first, I show relationship between participant measured cognitive ability in an experiment and their observed behavior in a laboratory experiment of the coordination game and an asset market experiment. And then I will discuss the strategic environment effect. And the purpose of doing this is to stimulate the discussion on macroeconomic implication of interacting among heterogeneous bounded rational decision makers. That's what Alan was also speaking about in a more philosophical perspective. I'm gonna do it with the data. And another perspective I want to give is to show how experimental and behavioral analysis can enrich macroeconomic analysis. Although this part is still, in an infant stage. Okay. So just to give you some definition of what I meant by strategic environment effect, which I'm going to be more in, towards the end of the presentation, that we say that strategic environment effect arises if the expected absolute deviation of choices from the Nash equilibrium. If you are in a macro field, you can replace this Nash equilibrium to the rational expectations equilibrium, is larger when the player's actions are strategic complement than when they are strategic substitute. So Alan was mentioning about financial market, etc., about when the heterogeneity may matter, but in a more precise definition that I give, it matters in a situation where there is a strategic complementarity and the financial market and the coordination problem are part of those problems. Okay, so this I will be more precise towards the end of my talk. Okay, so let me start with a simple experiment. Okay, so let's imagine the situation where you come to the laboratory and you are given instruction about the following game. So participants in this experiment are going to be divided into 2 groups, A and B. Okay, and 1A and 1B will form a pair and play a simultaneous move game. Okay, so you decide and another person decide without knowing what the other has decided. And A can choose either L or R. Those are the 2 options. And B can choose either U or D. Okay, so those are the 2 options. The payoff for A and B are as follows. So if A chooses L, regardless of B's choice, A obtains €8.50 and B obtains €3. If A chooses R and B chooses U, then A obtains €6.50 and B obtains €4.75. And if A chooses R and B chooses D, then A obtains €10 and B obtains €5. So imagine that you are A. Which option do you choose, L or R? So have you made up your mind? So think about which option do you choose, L or R. Okay. So I did this experiment in Paris. So this is a fraction of participants choosing R and over the 10 repetition. And this is done with a perfect stranger match, meaning that every time they play the game, they meet different people. So they are not repeating the same situation with the same opponent. So what this shows is that in the first period, only 50% of the people who chose A, 50% of A has chosen R. Okay, and this fraction goes up to 75%, and it's remained there. The question is, why don't all the A chooses R all the time? And I will elaborate this a little bit more. So this is a game that I showed you. Okay, so the B can choose between U and D, and A can choose between L and R. Okay, and these are the payoffs that I explained. So if you look at this for B, if B chooses U, he can get €3 or 4.75 euro, depending on what A does. And if he chooses D, he can get €3 or €5. So from B's point of view, he has a dominant strategy in choosing D, meaning that he cannot lose by choosing D, whatever the other person, whatever the A should, whatever A does, right? So if A believe B is going to choose his dominant action, which is D, then for A, it is simple choice between €8.50 or €10. So it is better for him to choose R. Okay. So as I showed you before, despite of this, not all the A chooses R. Okay. So one possibility is that there is an uncertainty about B's behavior. Although B has a dominant strategy of choosing D, not all the A believe that B is going to choose D. Okay. So that was a hypothesis to understand this result. And then we ran the new experiment to test this conjecture. So imagine that now you are in an experiment and you as player A, face a computer program that is acting as a B for 10 rounds. And this computer is going to act as follows. You are told that in addition to the rule of the game that I explained in the first slide, that the computer chooses D at each round without exception. So now you do not face any uncertainty about B's behavior. Okay? So for you as A, well, now the simple choice between €8, 50, and 10. So everybody should choose R. So that was our conjecture. And this was the result. Okay. So here is a result from the same game that I showed you. So blue is in a human that you saw before. And the red is in the case where participants are playing against a robot. Despite of our conjecture that all the A is going to choose R 100, all the time, 100%. We only saw 75% of A choosing R. Okay? That's a big disappointment. And if we choose a game, if we change the game a little bit, the situation is better. But again, even playing against the robot or the computer program who chooses D all the time, the human participant did not choose R 100% of the time. So we started asking who are those A in the experiment not choosing R against a robot. There must be something wrong with this participant, or maybe there was something wrong with our experiment. And then one thing that we have decided to look into was the cognitive ability of a participant. So there are several ways of measuring cognitive ability, but we have chosen one particular test called Raven's progressive matrix test. And the Raven's progressive matrix test is as follows. So you are shown this picture on the top. Okay, there are 8 pictures with one blank spot. Okay, and you are asked to choose out of those 8 options below that best suited to replace this blank spot. Okay, and in this particular case, you can say that okay, as you go down the picture, the number of the horizontal line increases, and if you move from the left to the right, then it becomes triangle to square, right? So now you can say from this pattern, maybe the best option to choose is 2. Okay, so this test has a logical structure, and this similar test is used for military and various places. And this is used to measure what they call fluid intelligence. And this is the ability to think logically without any background knowledge. Okay? So after doing this test, so we implemented this test at the end of the experiment. And then we categorize our participants into 3 groups depending on the test, the result of the test. The first group is low ability. So those are the 1/3 of participants who score at the bottom at the bottom. And the high ability participants are those participants who score 1/3 of the participants who score the highest. And medium is a between. And if you look at this, again, it's the fraction of those participants who has chosen R over 10 period. For those low ability guys, the fraction of those low ability guys who has chosen R playing against human or the robot opponent are the same. So there was no difference whatsoever. If you go to high ability guy, if they are playing against human opponent, the fractions are about 65%. If they are playing against a robot, this fraction goes up to 80%. So they respond to change in the characteristics of the opponent. The same picture can be shown not as the average fraction, but number of times these participants has chosen R over 10 period. So this is a cumulative distribution. So this 10 means that these are the participants who has chosen R 10 times out of 10 times. And 0 means those are the participants who has chosen R none of the times during the 10. And this red one is against a robot, and the blue one is when they are playing against human opponent. Again, the low ability guys, there is no difference. And high ability guys, as you can see, that if they are playing against another human, there's a large fraction of guys playing R none of the 10 times. And if they are playing against a robot whose behavior is known, they are choosing R 10 times out of 10. And so this is a big difference. So what you can see from this picture is that if you look at blue curves, okay, so against human B, these cumulative distributions are not different. So if you are facing the human opponent, their behavior do not differ. But if they are playing against a robot, then this frequency, as you can see, is shifting towards the right, meaning that higher ability participants are playing R more often. Okay. So what does this mean? This simply means that this problem of the coordination that Alan also mentioned, the coordination is big, and this is a coordination game. Even in this simple coordination problem, whether you can successfully coordinate or not depend not only on the what the uncertainty about what the other will do, but also whether you take that uncertainty into account. So these guys, when facing human opponent, they are afraid that the other people may not behave rationally, so they do not behave rationally. But if they know that the other person is going to behave rationally, they behave rationally. But low ability people, they don't respond against the different nature of the opponent, and they basically do the not the random things, but they behave non-rational way. And those high ability guys are basically worried about how these guys are going to behave. Okay, and this is kind of illustration of how the heterogeneity of the cognitive ability of the decision maker can have a different outcome in the aggregate. So this was about a simple coordination game, but let me now move on to a more exciting financial market experiment. Okay. So now consider the totally different experiment, and it's much more complex than the one that I showed. And this is what we call experimental asset market paradigm, or a la Barnum Smith et al. In 1988 Econometrica. So imagine the situation where N participant to the experiment is going to trade an asset in the market over known period, say 10, right? And each trader is initially given some unit of asset and some cash so that they can trade using this asset and the cash. And at the end of each period, a unit of asset pays a dividend of D. Okay? And the cash held before dividend payment generated an interesting earning at the rate R. Okay? So if you hold the cash, you get some interest payment. If you hold asset, you get some dividend. Okay, and the cash and the asset are carried over to the next period to be used in trade. Okay, and after the final dividend payment in period T, this is a final period, the asset is converted into cash at some rate, say B. Okay, and if you participate to this experiment, you will be rewarded according to the final cash holding. So the objective of this experiment for you or the participant is going to generate as much cash as possible at the end of final period. Okay. And in the simplest possible setting in which the cash does not generate any interest, so the cash you have is just a cash without any additional income, at the end of the experiment, the bond or the asset you have will lose its value. So the B is going to be 0. And the dividend is known and constant for all that period. Then you can compute the fundamental value of the asset as follows. Fundamental value of the asset from the at the beginning of period T is simply the sum of remaining dividend payment, meaning that at the very end, period T, what you can expect to receive from holding this asset is this final dividend D. So it's D. So that's the final fundamental value of this asset at the very end. And the period before that, you can expect to receive dividend twice. So it's going to be 2D, etc. So you can calculate back until the very beginning as a fundamental value. And in the finite time horizon, so that T is known, and as in a standard game theoretic analysis where everybody is rational and everybody knows that everybody is rational, etc., you can solve this game with a backward induction, starting from the very end and solve it back to the very beginning. Sorry. And then, sorry, maybe you don't see this final line here, but the price of the asset should be the same at the fundamental value from the very beginning to the very end. Okay. So if you do this experiment, what will happen? So this is a typical result. So in this case, T is 10. So there's 10 period of trading, and there's no short selling of the asset or no borrowing of the cash. So you have to trade with the asset and the cash you have. And in this experiment, there were 6 traders in the market, and dividend is known to be 12 experimental currency unit. And everybody at the very beginning of the experiment, they had 4 units of asset and 520 units of cash. Okay. So with this dividend condition, the fundamental value of the asset is going to be 12 at the very end, 24, 36, 48, 60, etc. And it should go to 120 at the very beginning. So the theory tells you that the price should follow 120, 108, 96, 84, etc. So it's a straight line down from the beginning to the end. But in experimental result, this line, connected line, shows the dynamics of the price in one market, and this is another in the market. The typical experimental result is such that the price at the very beginning of the experiment is below the fundamental value, and it's go above the fundamental in somewhere in the between, and it crashes back to the fundamental at the very end. Okay, so this is the first round result. And another well-known result is that if the same group of 6 participants repeat this experiment in the same environment twice or 3 times, they learn to trade this asset at the fundamental value. Okay, so as you can see that the deviation of the price from the fundamental value becomes smaller as participants repeat the same experiment. So this result is well known, and what we wanted to do is that to understand why this mispricing happens. Okay, and there were two main reasons proposed in the literature. One proponent is that this, what they called price bubble in the experimental asset market, is due to confusion or the irrational behavior by participants. After all, these are undergraduate students in a university who has no experience whatsoever, not whatsoever, but little experience in trading assets. So they are confused and they don't understand the fundamentals. The another explanation is uncertainty about other traders' behavior or the understanding about experimental setup. So this reasoning is that, okay, the participant knows or they understand the experimental setup. They understand what the fundamental value of the asset should be. But they are worried that other participants in the experiment do not understand. Therefore, they do not believe that the price will follow the fundamental value. Okay, so those two are a little bit of the different interpretation of the same result. What we wanted to do in this paper in 2017 was to measure how much of the mispricing that we observe in experimental market can be explained by the confusion and this uncertainty about other behavior. So how do we do that? The experimenters are often simple-minded people, and as an experimentalist, I also am a simple-minded person. So what we do is very simple. So let's construct this 10-period asset market with 6 traders. This is exactly the same setup as I showed you a few slides back. Dividend payment with 12 occupy period per asset. And we run experiment with 2 treatments. Okay? One treatment, the participant to the experiment trade the asset with 5 computer traders. And another in treatment, one participant trade the asset with 5 other participants. We call this treatment all human, 6H, because there are 6 humans in the market. And this treatment, 1H5C, because there's 1 human and 5 computers. Participants are told which treatment they are in. So if you are in this treatment, you know that you are trading against 5 other participants. And if you are in this treatment, you know that you are trading against 5 computers. Furthermore, the participant in this setup are told about how computer behave. Okay? And in order for you to understand what we told a participant how computer behave, I have to explain you a little bit about experimental setup. So let me go through that. So participants are given this table. So this table is basically summarizing the fundamental value of the asset. Okay. What we didn't use the word fundamental value, but use word next value. So the next value of the asset before the beginning of period 1 is 120. At the end of period 1, you receive the dividend of 12. Number of remaining period that you can receive dividend is 9. Therefore, the next value is 108, etc. Right? So participants had the table of the fundamental value at their hand, and they could check this anytime they wanted during the experiment. And this is an experimental market rule. So we use call market rule. What is this? Well, in this market, all traders simultaneously submit their buy and sell orders. So this is not the typical stock market. You see that orders coming in continuous time. So if you as a participant want to submit a buy order, you have to specify the price. If you want to submit sell order, you have to specify the price and quantity. And there were some numbering constraints because of the technology we used. But so in the experiment, all the traders are submitting either buy or sell or both of them at simultaneously, meaning that without knowing what the orders other participants are submitting. Okay. And once all the orders are submitted, then the buy orders and sell orders are aggregated to find the market price. Okay. So once having explained all this, we tell the participant in 1H5C about the behavior of the computer. We tell them as follows. In each period, each computer trader submit orders by setting both the maximum price it is willing to pay and the minimum price it is willing to accept for a stock equal to the next value at the beginning of the period. Okay. So they know that computers are submitting both buy and sell order at this price. Okay. So if you are not confused, if you understood this experiment, you can compute them. You can imagine the market price is going to follow the fundamental value in 1H5C because there's you alone in the market cannot influence the price. So why do we use this design? Well, because if you are a participant to this experiment and understood everything in the experiment, that's what we call non-confused human trader, you should expect the price to follow the fundamental value, right? So if I observe any deviation of your price expectation from the fundamental value, it must be due to some kind of confusion of participant. Okay, they did not understand some part of the explanation or the experiment. Okay, let's take the non-confused human trader in all human market. Okay, he understood everything about the experiment, but he may not expect the price to follow the fundamental value because of the uncertainty about others' understanding or others' behavior. So if I observe any deviation of his expectation from the fundamental value, this must be due to the uncertainty about others' behavior and some kind of this person's own confusion. Right? So if I take the difference between these two treatments, in 1H5C, all the deviation comes from the confusion. And in 6H, it's a combination of behavioral uncertainty and the confusion. So if you take the difference, I can cancel the confusion out. So I can isolate the effect of behavioral uncertainty. So this was the aim of this experiment. And here is let me go through. So here is a result. So what we measure is the deviation of price forecast from the fundamental value. And I'm summing this over for 10 periods. Why? Because at the beginning of each period, we ask participant to submit his price forecast for remaining period. So in period 1, this participant is submitting his forecast for period 1 price, period 2 price, period 3 price, etc., up to period 10. Okay, and in period 1, he just received the instruction and he did not trade with the other trader. So in that sense, only difference between 6H and 1H5C is the instruction about who are the other traders and how the computer traders behave in this treatment. Okay, and now I have CLT 1, 2, 3, and this is again in order to categorize the participants depending on their cognitive ability. What this score means is the number of correct answer in cognitive reflection test. What is cognitive reflection test? This is a very simple 3-question problem that you may have seen somewhere. So for example, one question is that a bat and a ball cost $1.10 in total. A bat costs $1 more than the ball. How much does the ball cost? The intuitive answer is 10 cents. Okay, but the correct answer, as you can, smart people can calculate, is not 10. So in order to arrive at the correct answer, you have to first reflect upon your intuitive answer. So that is why it's called cognitive reflection test, right? So there are 3 questions of this sort. And then I computed the number of correct answer participant gave in this test. So as you can see, there are some participants who scored 0 or 1. So this we call as a CRTS less than or equal to 1. And there are other participants who scored perfectly in this test. What you see here in red is the distribution of what I call relative absolute focusation in 6H treatment, and blue is in the 1H5C treatment. So everybody is rational, and there's no effect of the confusion or the behavioral uncertainty. This deviation should be 0. So everybody have the distribution on the y-axis. This difference between the y-axis and the distribution is the effect of the confusion or the behavioral uncertainty. In case of perfect CRT score guy, so these are really smart people in our participant. On the blue, if they are playing against computer, deviation from the fundamental value is quite small, right? If they are playing against other human, these are the red, the deviation is quite large. So this difference is what is the behavioral effect of behavioral uncertainty. Again, the interesting finding happens, right? So those participants who had a low CRT score, there's no effect of behavioral uncertainty. Everything is about confusion. They did not understand some part of the experiment. Those guys who are smart, if you compare this red of the low CRT score guy and the CRT3 guys, these are not statistically significantly different. So the total impact of the behavioral uncertainty and confusion are the same for all these score guys, but the effect of behavioral uncertainty is much higher for those smart guys, right? So interesting, again, just to summarize, the both confusion and strategic or behavioral uncertainty are important, but this importance of each component depend on the cognitive ability. So the effect of strategic or behavioral uncertainty is much larger for smart guys, and for low CRT guys, so not so smart people, it's all about confusion. It's a very similar result with the 2 simple coordination game I talked about in the beginning of this talk. Right? So with 15 minutes remaining, let me move on. So Alan talked about heterogeneity and interactive agent and its impact, its potential implication to macro, right? So what we want to build upon is that now I showed experimental evidence about impact of heterogeneity in the cognitive ability on the deviation from the Nash equilibrium or the rational expectations equilibrium. And there are some nice models out there to think about or to organize our thinking in when the heterogeneity is heterogeneity among decision makers are about the cognitive ability. Okay. And then these are what is called level K by Rosemary Nagel, or cognitive hierarchy, the Colin Camera and his co-author models. So what this model tells you is that the level 0 agent, so there are several agents with the different levels. So level 0 agents make very naive choice, okay, without thinking about opponent. For example, doing random things or not, just picking option randomly, for example. And level 1 guys are a little bit more sophisticated, and they consider about others. So level 1 guy consider that others are level 0, okay? They are less smart than themselves, and try to best respond to the existence of the others. And level 2 guys think that others are either level 0 or level 1, and think about what those people will do and best respond to those other guys. So now what I want to talk about, what are the potential macro implications of such heterogeneity? And first of all, what I want to talk about, when does it matter, if at all? The traditional economics, what Alan was criticizing, was basically assuming that, okay, this heterogeneity we can forget about because market solves everything, okay? But what I want to propose is that those are only true when the the behavior are strategic substitute, and that is not true when the behavior are strategic complement, which I will define more precisely in the following slide. Okay, to show this, let's think about the simple game, what we call beauty contest game, and we're going to consider the two versions of beauty contest game. So in the general setup, let's imagine a group of n subjects simultaneously choose a number between 0 and 100. And the winner is the subject who has chosen the number closest to the target number that's going to be defined below. And if there are several winners, we're going to be randomly picking one of them. Okay. So the target for person I in BCG plus game is that 20 plus 2/3 of the average number chosen by everybody else. Okay. So this is BCG plus game. If you are playing BCG minus game, the target is going to be 100 minus 2/3 of this number chosen by other people. Okay, so those 2/3 of the average number chosen by other people are just common in these two games, but the other components are different. Okay, so why are we doing these two games? If we look at the step-by-step best response in these two games, there's some interesting result, interesting aspect. So let's start the station in which that you believe everybody is choosing 100. Okay, you believe everybody is choosing 100. So what is your best reply? In a BCG plus, if everybody is choosing 100, this mean minus I is 100, right? So the target is going to be 20 plus 2/3 of 100, which is about 86. Okay. And now, if you believe that everybody is choosing 86, the target is going to be 20 plus 2/3 of the 86, which is going to be somewhere around 60 something, right? And as you go along, if you increase the number of steps, you approach 60, which is the Nash equilibrium of this game, from one side of the equilibrium, smoothly, gradually going down and reaches the 60. In case of BCG minus, the same thinking process will lead to different outcome. So if you believe everybody is choosing 100, the target is going to be 100 minus 2/3 of 100, which is going to be 34 or something. Now, if you believe that everybody is choosing 34, the target is going to be 100 minus 2/3 of 100, which is going to be 70 something. I forgot the exact number, but it coincides with the target with BCG plus. And as you go along with this thought process, you approach again the Nash equilibrium, which is 60, by alternating up and down around the equilibrium. Okay, and the same things you can do wherever you start. Unless you start with the 60, there are differences between the BCG plus and BCG minus. Okay, so here is the experimental result, and then let me explain why we did this experiment and what did I mean by strategic substitution and strategic complementarity. So these are the different number of people in a group, participant in a group. N equal to 2, N equal to 5, N equals 16. So N equals 16, the largest group we considered. So there are 60 participants in one group. What we show here is a distribution of absolute deviation of a participant choice from the Nash equilibrium, which is 60. So if everybody chooses 60, then the distribution is on the y-axis, right? And the red one, which is solid, is BCG minus. Its target is 100 minus 2/3 of the average. Blue one, dashed, is the deviation from the BCG plus, which the target is 20 plus 2/3. As you can see, the deviation from the equilibrium is larger in dashed one, which is BCG plus, when the target is 2/3, 20 plus 2/3 of the average. Okay, so why do we get this result? Well, this is what I called a strategic environment effect. So the effect of non-strategic play, like people, the participant not understanding the game or doing something random, can manifest in aggregate under strategic complementarity, but not under strategic substitutability, because of the way sophisticated player best respond to the naive player. Okay, this was old definition from Haltiwang and Waldman in 1985, but as let me elaborate on this a little bit. So the strategic complementarity versus strategic substitutability. So strategic complementarity means what? Strategic complementarity means when you believe that others are increasing their choices, you also want to increase your choice. Okay. So this is BCG plus, right? If you believe that others' choice is going to go above, you also want to increase your choice. Strategic substitutability is the opposite. You want to do the opposite of what the other you expect the other will do. So if you believe that others are going to choose a higher number, you want to best reply by choosing the lower number. Okay, so that's the difference between strategic complementarity and strategic substitutability, and that is important in this setup by considering several levels, right? So let's imagine the situation where level 0 chooses 100. This is a simple illustration. Okay? So these guys, his deviation from the Nash equilibrium, which is 60, is 40. So which is the same between the BCG plus and BCG minus. Level 1 guys are best responding, believing that others are going to choose 100. In BCG plus, that will lead to 86.666 with the deviation from the equilibrium 26 point whatever. And in BCG minus, the choice is going to be around 34 with a deviation around 26, which again is the same between BCG plus and BCG minus. But higher level guys, these are different. Why? Because level 2 guys believe that others are level 0 and level 1, or either of level 0 or level 1. So when deciding what to do, he computes the average between the choice between level 1 and level 0. Okay, and as a result, he chooses 82, which is quite large compared to the Nash equilibrium. In a BCG minus, again, the level 2 guy believe that others are either level 0 or level 1 and take some weighted average between these two numbers to compute the best reply. As a result, his choice is going to be 55, which is much closer to the Nash equilibrium compared to the BCG plus. Okay, so this statement, effect of non-strategic play can manifest in aggregate under strategic complementarity. Yes, it does manifest under strategic complementarity. Why? Because at the lower level, under the strategic complementarity, the deviation from the Nash equilibrium does not cancel each other out. Right? In a strategic substitution, these two cancel each other out and it does not manifest in aggregate. Okay, so let me summarize what I've been talking about. So the strategic environmental effect and macroeconomics. So when there exists strategic complementarity among choices of decision makers, micro level bounded rational behavior can have large macro impact as individual deviations do not cancel each other out. This was the result that I showed you with the beauty contest game. Okay, so that was a very simple game. You can ask, what does this do? What does this have to do with the real economy? But just imagine, what are the situations characterized by strategic complementarity? Well, these are the situations in which coordinations are important. Remember what Alan said. Alan said economics what we should be looking at is not about efficiency, but more about coordination. Okay, if the coordination is important in economic activity, well, the important economic activities are more often characterized with strategic complementarity. Right? The financial market is the same. Right? If you believe that the price of the stock is going to go up, what would you do? Well, you don't sell today, but you buy today, right? So it's a strategic complementarity again. The macroeconomy is the same. If you believe that the economy is going to be boomed, you want to invest, which contribute to the further to the boom, right? So we believe that the macroeconomics thinking that these are the situations in which the strategic complementarity is playing an important role. So therefore, the heterogeneity in terms of cognitive ability among decision maker is also important in this situation. Okay. So having said that, we should start rethinking about macroeconomic theory, which ignores the heterogeneity and often assume rational, homogeneous decision maker, what we call rational uh, representative agent. But we should move away from it, and we should move into more heterogeneous interactive agent framework. And you know, I was a former colleague of Alan, and we were thinking about this all the time. And we thought, as a previous question arises, mainstream economists are not very excited about this type of idea. But well, things are changing. For example, in 2019, American Economic Review, Farley and Werning, who are the professor at MIT, they published an article combining level K argument with incomplete market. And then he showed that, okay, there is a limited effectiveness of monetary policy which cannot be explained with homogeneous rational agent or the complete market. Okay, so once you deviate from homogeneous rational agent, you can start explaining a lot of macro phenomena as these authors have started to do so. Right? With this, I'm gonna close my talk, and I have 2 minutes remaining. I'm not quite sure what we should do, but I pass this back to you, Ren, if you are still around. So thank you very much for listening to my talk. So any questions are welcome.
Thank you. I learned more from that than I learned in like half a year of game theory. So yeah, that was really informative. Thanks. We've got questions here that I'm just going to read out very quickly. We only have 1 minute left of the session, but we've got two very good ones. I'll just try to get through both of them quickly. So recently, electronic platforms have been giving more and more access to economic markets, e.g., the stock market, to the general public. Are you aware of this resulted in a change in behavior in those markets? And if more and more people are allowed to participate, does this increase heterogeneity? And can you predict any effects this might have on the real world?
Okay, so that's a very good question. So it's an anecdote. I haven't done the serious analysis, but at one point in Chinese stock market where it was booming quite a lot, there was a newspaper article saying that more than 50% of new investors in those markets, the highest academic degree is the highest education they have attained is a primary education. And for 8% of them, they cannot even read. Okay, imagine the stock market in which majority of people with the primary school education. Do you ever imagine that whatever the things that we think in the national expectation equilibrium would be happening? So as a result, as you can see in the Chinese stock market, it's boomed and there was a bubble, right? Can we predict any effect of this might have happened in the real world? Okay. So I would imagine that this will increase the tendency to herd. So the volatility should increase because herding behavior will increase the volatility of the market. All right. And so volatility of market increase, which also means that the market will be more uncertain, right? So the prediction will be harder. But only thing that we can predict is the higher volatility and the instability of the economic outcome. So that's what I would say. Any other?
And we have another one. Do you think there might be positive sides of using people that are inexperienced in being experiment subjects?
Positive side. Okay, so I think there is number one that in a situation where things are changing rapidly, for example, COVID situation, or in even the stock market bubble situation, the what we call the dot-com bubbles, when when people are facing something new, a new technology, or a new situation, we are all inexperienced, right? So that's where we can learn a lot from the experiment using inexperienced subject. Okay, if you want to learn the situation in which experienced subject experience how the experience uh, influence the behavior, yes, we can repeat the experiment several times and see how people learn to behave in such market. So that's, I think, is a great advantage of using inexperienced subject in the experiment to study how the reaction of people in unknown situation or new
Okay.
situation, I would imagine. Yes.
Okay. Those were the two questions. Those were beautifully
Mhm.
answered. There was one more, but I think that we're running a bit over. So
Mhm.
yeah, I think we'll leave it there.
All right. Thank you very much.